order to, as I said before, we have an engineering problem. Okay, then engineering problem has to be converted into the mathematical model. Mathematical model then has to be solved using the numerical model, and then we come up with engineering solution. For example, right now our engineering solution is we want to know the behavior of the pressure. Okay, pressure over time, or pressure at certain distance over time. So this problem, engineering problem, we will tell to the mathematical models. We will develop the mathematical equations for that. Mathematical equations will be solved by mathematicians using the numerical methods. We have few numerical popular numerical methods, and we have so many programming models that can solve the mathematical equations. For example, finite element, finite difference, which is the most famous. Using that one, we can sort out our issues. And in the upcoming lecture, we will talk in details about the mathematical models and numerical models and so on. Now, first of all, we need to look at it. What are the fluid and rock properties of the reservoir? Uh, let's look at the steps that we are talking in this slide. For example, conversion to mathematical model require understanding physics. Well, you need to understand what kind of fluids you have, because as you know that we have different kind of reservoirs. You have gas reservoirs, you have oil reservoirs, but you have reservoir which has oil and gas both, and then you have oil reservoir which has water, and then you have the gas reservoir which has water, and then you have the oil reservoir which has gas and water both. So we have so many kinds of reservoirs, and starting from the dry black oil, and if you remember from the reservoir engineering, we have retrograde condensate, we have the combination, we have dry gas, wet gas, and so on. So we have so many types of reservoirs that we have, and we have to look at it what's going on. Then we have to look at the flow, and for flow, as you know, in reservoir engineering we use Darcy's equations. So we have to describe their flow. We'll have to look at their properties. These properties, fluid, rock, the flow, and the transport of those, we convert them in the mathematical equations using the conservation of mass, energy, and momentum that we are going to discuss in the upcoming slides. Then this has to be solved using we will get the partial differential equations that has to be numerically solved. We will talk about it in the upcoming lectures, a lot about it, and we have to find the mathematical solutions in order to to get what the good reservoir simulators. So in this case, you can say that we have three steps: the physical models, we convert them to the mathematics, then after that we have a numerical model, and then so on. Then you can see here what we do in reservoir simulation. We have a big reservoir here, but you see that uh, here it is not uh, it's just a one block. Let's say it's from here to here is 2 kilometers, and from exactly, maybe let's say from here till here, let's say is 2 kilometers. But for example, now you want to know the pressure at this point, at let's say at this point, or you want to know exactly what's going on at this point, or you want to know what's going on at this point. So what we do, we break this kind of uh, reservoir into the blocks. You see here, 1, 2, 3, 4, and 5. These 5 blocks. We call them blocks. You can call them grids. You can call them cells, or you can call them elements. Usually, what we do, we call them grid blocks or grids. What we do, we write an equations for pressure, saturation for each block. As I said in the first introductory, very beautiful picture, that we have to write equations for each block, each cell. And saturation means how much the oil is present exactly at this point. I mean, how much is the the gas is present at this point. As you can see that there may be oil here at the top, maybe at the bottom we don't have oil. So we have to look at it, what's going on. Then these equations, we get set of linear equations, and we solve them in the next step. So let's go ahead, and we look at some mass balance. We look at what is going inside and what is going outside, and what is accumulated inside for each component, for oil, gas, and water, and energy, and so on. Now, in order to develop the reservoir simulators, actually as you know that we have three phases: uh, oil, gas, and water. Well, you can argue that oil and water both are liquids, but since we are interested in oil and not in water, so we consider them as separate phase because of their densities, and our objective is to produce the oil. So we consider them as separately. Then, as I said, in the reservoir is three-dimensional. We have flow in X, we have flow in Y, we have flow in Z. These are the issues. So three dimensions, three flows, three phases. It's a very, very complicated equation. So in this course, we will develop some equations for you in order to give you just a flavor that how this reservoir simulation works. So we stick to one phase, let's say the oil. We stick to one single linear flow direction. As I say, we will talk about the in and we talk about the out. We don't talk about the direction which is going on here or here. But in the real simulators that we have used, or they have three dimensions, and they have three phases, and they talk about the grid system, which is linear. Some uses the radial, and so on. So basically, in bachelor's degree, one phase is to give you a flavor is fine, but when you go for masters, and you will definitely look for two phase and three phase and so on. Look at the equation that we have. We have a partial differential equation, and which is the mass balance, and we are going to talk about these equations in much details in the upcoming equations and so on. So now, in order to write an equation, what mathematical needs we need? Well, you need root finding, especially the linear system of equations, integration you must know, differential equation. So this is the calculus background that you need to know in order to. Then after, once you know the root findings, and you can develop some equations, and you know the integration, derivation, the differential and partial differential equations. You can develop the programs. There are so many programming softwares like Python, and the MATLAB and C++ and Fortran, still the legendary software, which programming software, which still is very popular. Now the question is, okay, now we have Eclipse and CMG. Why we need to look at the equations, and why we need to develop the mathematical softwares? And why not we just use the commercial softwares? We have many commercial softwares, let's say the Eclipse and CMG and so on. And why don't we use them simple? Well, these we have to look at the philosophy. And by the way, the each big company, especially the big four or big five companies, including the Aramco and Chevron, and they have their own inbuilt homemade softwares for reservoir simulation. Why? Well, because simulators have lots of limitations. Well, they can give you a very misleading results. So you have to understand, when you use the simulator, you must first know at what mathematical and physically process they are made of. Maybe they are made of some reservoir made in Texas, and you are in Dammam, and Saudi Aramco is using those softwares where the geology and everything is very different. So what the results it gives in Texas may be correct, but same results maybe their processes may not fit in with the Aramco. So what Aramco do in this case, they are only hires PhDs. They have a research department. They have so many PhDs with experts of mathematical modeling and reservoir modeling, and they develop their own in-house softwares, and that's what is going on. Well, now who knows, you might be the smart person that creates the next commercial device simulator. Well, if you are reaching, you're understanding this course very nicely in this undergrad level, who knows that in masters and PhD, or maybe in an oil company in future, you are going to develop this reservoir simulators for a particular reservoirs and so on. So here you can see, there's so many wells we have shown you here. Look at this model. It looks very beautiful, but it's very, very complicated, and so many processes, so many wells, so much data we have. This blue you can say is the water. This we're talking about the water saturation. This yellow upper portion has some oil, gas, and so on. So what it does, it builds. We have to predict. We have to know that, okay, after 1 year, how much oil we are going to produce, and currently softwares have only limited range of solutions for a particular reservoir problem. Well, every year the new update version of software is coming, which has latest researches included, latest data included. But every year the software is updated, and because every year the new things are coming up, and so on. So on. Well, when we talk about uh, the reservoir simulators, make sure that you're data is correct. Garbage in, garbage out. Okay, this is the simple thing. GIGO, computer program. You need a reliable data. You have to, you must make sure that your data is reliable. So the companies, oil companies, the reservoir engineers, they spend more time on finding the reliable data than on the simulation itself. The data has to be reliable. For example, the porosity in the simulator, you input your reservoir porosity is 25%, but actually it is 20%. So it will give you an error. I mean, you predicted that you have an oil of, let's say, 10,000 barrels in your reservoir because the porosity you mentioned is 25%. Actually, it was 20%, and then the real reserves are less because the porosity is less. So the data has to be correct. The data has to be correct. If wrong data, garbage data means garbage results. You cannot rely on those results. So the first thing the company will ask you, the bosses will ask you, do you have the reliable data and how much you are sure about it? Do you rely on your lab's results and so on? So you have to be very careful in that. As I said, we have some commercial softwares, CMG, Eclipse, Intersect, Schlumberger, and Chevron, and the Nexus. In our course, we will stick to this Eclipse software, and then, as I said, many in-house softwares, Empower, Cheers, BSM, Morris, and Saudi has the power. So as I said, these companies, they have made their own in-house softwares that